Oh, hello everyone. Welcome back to another video. I'm back with, well, this is now my third calculus video of this YouTube channel. If we have this integral here, let me just set up my stuff. This is the integral. I'll read it out. The limits from 0 to pi over 2 of 1 over 1 plus cosine of x dx. How do we do this? Now, I want to show you like multiple ways to do it. I'll show you, well, firstly, if you want to look at my previous video, I had given you the proof of the following integral, 1 over a plus b cosine of x dx. I used a Weierstrass substitution to prove that this equals 2 root a plus b over a minus b all over a plus b multiplied by the arc tangent of x over 2 over root a plus b over a minus b, of course with the plus c at the end. And we could technically use this proof that whatever I did to prove this to work out the integral that we have for today. But there is one issue. Now, you may wonder, to get from this integral to that integral, what have I done? Well, firstly, that's my a, and here my b is there as well. A and b, I've made them equal to 1. What's the issue of this? The issue is if you plug in a and b as 1 into this bit, for example, let me just zoom into this, you get 2 root 1 plus 1 over 1 minus 1, which is equal to 2 root 2 over 0, and that's where the issue lies. We're not allowed to divide by 0, so what are we supposed to do with this? Well, I have an answer for you, and that answer lies in calculating stuff using limits. So let's use some limits, and you get some crazy cool stuff. It's not difficult for you if you're in like Calc 2 or in further maths A level, but we'll see how it plays out. So let's say that our integral, is equal to well, we've let a and b equal to 1, so it's equal to the integral from 0 to pi over 2. In fact, I'll just write straight away 2 root 1 plus 1, which is 2, over 0. Instead of writing over 0, I don't want to abuse notation, so I'll just use a new variable. I'll call it u. Why not? 2 over u, and then a plus b is equal to 2, and we have arctan of tan of x over 2 over root, once again, 2 over u. And then instead of putting down a plus c at the end, because this is a definite integral, we should put down some limits. I'll just use this notation here, evaluated at 0 and pi over 2. Okay, and I'm forgetting one more thing. We need to limit as u approaches 0. How are we meant to do this limit? Well, firstly, let's work on oh yeah, these 2's, they cancel. I'll just do that in green, why not? Let's work on the fact that we have to sub in these two limits into x. Sorry. So this will just equal, I'll write everything in black, root 2 over u, arctangent of, I'll write, so you see this bit here, this square root, this is technically equal to 1 over the square root of 2 over u, which can actually be written as the square root of u over 2, because of rules of fractions and stuff, where you have 1 over a fraction is equal to the reciprocal of that fraction. and this applies even if we're talking about square roots. So in reality we have u over 2 multiplied by the tangent of x over 2, but since we have limits, we must work out what this evaluates to when x is equal to pi over 2, so tangent of pi over 4. And also, if x is equal to 0, tangent of x over 2 is tangent of 0. And then we are one step closer, pretty much, to finding out our limit. Of course, I keep forgetting to put down the limit as u goes to 0. Okay, so the integral is equal to, once again, the limit as u approaches 0 of that surd multiplied by arctangent of what's in this bracket. Well, firstly we have root u over 2, no dispute about that. Tangent of 0, if you draw the tangent graph, is equal to 0. We cross that out. Tangent of pi over 4 is equal to 1. So this entire thing is equal to 1. So we just have this really. Arctan of root u over 2, basically. And let's write this in the following form. The limit as u approaches 0 of arctan root u over 2 all over root u over 2. What have I done? How did I get this? Well, once again, what I did was I brought this fraction, put it into the denominator, and reciprocated it. Simple as. The reason I did this is so we can use something called L'Hopital's rule. I keep spelling it wrong. So this rule states that if you have some limit of some variable approaching some constant of two functions of that variable divided by each other like that, this is equal to the same limit of the same variable to the same constant of, the only difference being the two functions differentiated in respect to that variable. If I were to use this principle, this limit here, this limit, all I would need to do is differentiate the numerator, differentiate the denominator, and make it easier for myself to work out the limit. What's the purpose of using this rule? Well, if we were to sub in u immediately into our limit, well, if you sub in u into the numerator, that's not a problem. You get arctan of here, arctan of 0, which is equal to 0. That's not a problem. The issue lies in subbing the u into the denominator. You get root 0 over 2, which is 0. And you end up dividing by 0, which is kind of illegal. So you end up with a 0 divided by 0 situation. And that is indeterminate. It could land you quite a hefty penalty. Anyway, so let us use L'Hopital's rule to differentiate the numerator and the denominator. Let's first differentiate the denominator because it's much easier. So root u over 2, I'm going to use prime notation. You could also write d over du like this, why not? But today I'm going to use prime notation just to spice it up a little bit. This is equal to root u over root 2, which is equal to root u times 1 over root 2. Of course, prime. Not like the drink. Just this is a little bit better, you know. This is calculus. So I'm going to rewrite this as 1 over root 2 u to the power of a half. Actually, you know what? I'll rationalize the denominator of the set. So root 2 over 2 u to the half. And if you differentiate this, you end up with root 2 over 2 multiplied by half u to the negative a half, right? And if you simplify the fraction, you get root 2 over 4 u to the negative a half. I'll just put the u to the negative a half as a surd on the denominator. So there's no problem in this at all. This is quite simple. How do we differentiate the numerator then? So arctan of root u over 2, all differentiated, so prime. Well, let me just write something quickly in green for you. So if you were to differentiate in respect to some variable, let's call that variable, I don't know, let's call it x. So d over dx multiplied by arctan of x. If you differentiate arctan of x, you get 1 over 1 plus the input x squared multiplied by the derivative of x, which is 1. So actually, in fact, I have a better idea. To make it as general as possible, let's replace x with f of x. So arctan of some function of x is equal to 1 plus that function of x squared, like this, multiplied by the derivative of that function, or basically the derivative of the argument of the arctan. So that's what we're dealing with. How do we use that principle? In our situation, instead of having f of x, we have root u over 2. 1 second, I made a little blooper and I'm happy I caught it, because otherwise it would cause a massive problem. The root has to be across the entire fraction. So if you differentiate this with respect to u, of course, you get 1 over 1 plus the argument, which is root u over 2 squared, meaning that the root and the squared cancel out. You end up with just u over 2. And this is multiplied by the derivative of the argument. And luckily for us, the derivative of this inside bit we've already calculated here on the right hand side. So we can just pretty much copy paste that. I'm not going to bother to copy paste it, I'll just rewrite it. So root 2 over 4 root u. Okay, so now I'm going to rewrite this limit after applying L'Hopital's rule. So therefore our integral is equal to the limit as u approaches 0 of arctan of root u over 2, like this, over root u over 2. This is the same as saying our integral is equal to the limit as that same u approaches the same constant 0 of the derivative of the top and the bottom, which is equal to the derivative of the top is 1 over 1 plus u over 2 multiplied by root 2 over 4 root u, and this is all divided by the derivative of the bottom, which is root 2 over 4 root u. Now the reason I wrote it like this is so that this bit and this bit cancel and you're left with this over here. So our integral, just a reminder, our integral, if we go to the very top, is this one over here of the function 1 over 1 plus cosine of x is equal to the limit as u goes to 0 of 1 over 1 plus u over 2. And now there's no problem in subbing in u equals 0 here right away, because you don't get some indeterminate form. You get 1 over 1 plus 0 over 2, which is 1 over 1 plus 0, which is 1 over 1, which is 1. So therefore the integral from 0 to pi over 2 of 1 over 1 plus cosine of x dx, using the thing that I worked out the previous video, is equal to just 1. How cool is that? Genuinely it's fascinating. Okay, so that's one way of doing the integral. The next way of doing the integral is, I think it's much better. It's the quickest way. The quickest way to do the integral is to scrap out the axiom we assumed from the start. What did we assume? We assumed that this statement over here was true. Now, we are allowed to assume some things. The reason I made that assumption is because I proved it in the previous video. You know, if you want to see that proof, check out my previous video. I think I uploaded it last week or something. It's not too difficult to find, given that I've only uploaded, this is my third maths related video, so it's not hard to find. So take your time out. That thing is only like 20 minutes or something. I mean, when I say only, it's, you get the point. So the next way to do this integral is using the Weierstrass substitution just straight out of the box. So just as a reminder, the Weierstrass substitution states that let's define a new variable. Let's call that variable t. Why not? T for tangent, t for Weierstrass, t for I don't know. So tangent of x over 2. And if you're like starting to question my capabilities, how did you go from cosine of x to tangent of x over 2? What is your logic? Well, I'll show you. Firstly, we need three things. We need cosine of x in terms of t, we need sine of x in terms of t, and dx in terms of t. Let's do the latter first. So to find dx in terms of t, the easiest thing to do would be to apply inverse tangent or arctangent to both sides. And you get arctan of t is equal to x over 2. Just one thing that caused a little bit of fiasco in the comment section last week was relating this and this. Well, this is just a quick reminder. These things are the same thing. So I just use the one on the left because the one on the right can sometimes be confused with this, all to the power of -1. This is different. This is actually equal to cotangent of t. This is not the same as arctangent. Cotangent, arctangent, they're different things. That's why I use that personally. And once again, you're allowed to use the notation with the -1. Sure, why not? You know, it's allowed. The guy at Black Pen, Red Pen does that. Other people do that. I just do this because, like, I'm trying to be different, you know, and all out there. Now let's multiply both sides by 2. So 2 arctan of t is equal to x, and now if you differentiate both sides, dx is equal to dt multiplied by the derivative of 2 arctan of t, which is 2 over 1 plus our argument t squared. This is the same as just what we did just now. So now if I were to draw a triangle that give me a little second. I'm just changing my setup. Okay, now it's better. Yes. If I were to draw a triangle which satisfied our substitution statement, this is a triangle with a right angle, and our critical angle is x over 2. And what is the definition of tangent? Well, tangent is literally just the opposite side of a right angled triangle over the adjacent. So we're basically saying the opposite over the adjacent is equal to t. So that's what this satisfied. And then let's use Pythagoras' theorem to work out the hypotenuse, and we get that root 1 plus t squared. So this triangle kind of implies that the sine of x over 2 is equal to the opposite of the angle, which is t, over the hypotenuse, which is root 1 plus t squared. And also that cosine of x over 2 is equal to the adjacent, which is this one, 1 over the hypotenuse, 1 plus t squared. Okay. What do we need? We need cosine of x, not cosine of a half of x. So let's utilize the double angle formula. Same thing as last video. I'm just repeating this to remind both of us. I'm quite forgetful. Cosine of x is equal to cosine squared of half of the angle minus sine squared of half of the angle. So this means that cosine of x is equal to, well, what is cosine of x over 2? That's what we worked out over here. These two things we're going to need. 1 over root 1 plus t squared. And of course all squared. If I do this in one go, you're basically squaring the numerator and squaring the denominator. If you square 1, you get 1. Nothing special. If you square the bottom, the square root cancels out. So I can write it like this. And let's do the same thing to the sine. Sine squared of x over 2 is equal to t over root 1 plus t squared, all squared of course. If you, whoops, not to the power of t, what am I doing? If you square the top, you just get t squared. And if you square the bottom, the square root is disappeared. So cosine of x is then equal to 1 minus t squared over 1 plus t squared. And now we can rewrite the integral in terms of t. So I'll rewrite it first in terms of x. So it goes from 0 to pi over 2 of 1 over 1 plus cosine of x dx. This is equal to the integral from x is 0 to x is pi over 2 of 1 over 1 plus whatever cosine of x was in terms of t, this buddy over here, 1 minus t squared over 1 plus t squared, and dx, if we scroll up, is equal to 2 over root 1 plus t squared dt. Not root, it's just 1 plus t squared dt. I remember in my previous video I made a little mistake about that. I did end up correcting it, not nearly correct, I fully corrected it, but it was a close call and I don't want to repeat that. So our integral is then equal to, if we take the 2 on the outside because it's a multiple constant, and then we can rewrite the limits from x is 0 to pi over 2 in terms of t. Now just a reminder, t is equal to tangent of x over 2. This means that if, let's write t as a function of x rather than its own variable. So t of x is equal to tangent of x over 2. If you sub in if you sub in x equals 0, you get t of 0 is equal to tangent of 0 over 2, which is 0, and tangent of 0 is also 0. And if you sub in pi over 2, you end up with tangent of pi over 2, which is pi over 4, which is 1. So our limits end up being evaluated as t equals 0 and t equals 1. And then we have the inside function part. So this 1 plus t squared on the denominator, if I mark it in red, I can distribute it into the other fraction. So I end up with 1 times 1 plus t squared, which is 1 plus t squared, multiplied by that complex fraction bit over here, multiplied by 1 plus t squared, where you see these 1 plus t squared terms cancel, and you're left with 1 minus t squared. And the fun part is that these t squared terms, they cancel. And so you're left with the integral, two lots of the integral, sorry, from the limits 0 to 1 in terms of t, of 1 over 2 dt. And this 2 and this half, they both disappear because they multiply to get 1. So you end up with the integral of 1, which is t. And the limits are from 0 to 1. And if you sub in those limits, you get 1 minus 0 equals 1. Therefore, the integral that I'm going to rewrite for literally the 50th time is equal to 1. So that's the second way of doing it. Just to remind, the first way we did it was using the theorem that I proved in the previous video. Is it original? Has someone else done it before? I might be the first one, which is not, it's no mean feat, but the point is it works, even in literal situations where you break maths and divide stuff by 0, for which you have to use calculus and apply limits. Now, what is the third method I wanted to show you? The third method is the longest and the most fun. Well, perhaps the length of time something takes is not exactly proportional to the fun you get out of something, but we're going to do it nonetheless. So let me rewrite the integral again. Dx like this. Okay, so that's our integral. What is the third method I want to use? Well, I want to use the very famous trick that I used in the first video called Feynman's technique. Now to do that, we must create a new function and define a new variable. What should we call that variable? I elect to call it capital A. But you could of course call it fish if you wanted to. So basically this thingy here, that is fish. Yeah, I'll just call it A because like I don't know, I'll just call it A. So the idea is we want, why does my pie look like a cake? Okay, that's better. So our idea is our two variables A and X are independent of each other, so they don't affect each other. So you're gonna have to use partial derivatives. Let's define our integral function as well. Let's keep the denominator the same first of all, and the numerator, instead of having just a lonely 1, let's have a 1 plus a lots of sine of x. Now the idea behind this is because, well, before I tell you the idea behind this, all of this implies that if I let a equal to 0, I end up with the answer to the integral that we are trying to work out, because 0 times sine of x is 0. 0 times almost anything is 0. So the idea behind this trick is to differentiate both sides with respect to a. So I'll just mark that in green for you here. I'll just put d over d capital A on both sides like that. And so on the left hand side, what you get is very, very basic, very obvious. Perhaps you wouldn't know if you were in year 11, but now you do. So on the right hand side, if we were to bring this d over dA into the integral, you would end up with a partial derivative with respect to a. Now the partial derivative, once again, it assumes that the x variable is independent of the a variable. So when you're doing a derivative with respect to a partially, you assume x is a constant. So what do we do here? Let me just rewrite the partial derivative part on the right hand side for you. So the partial derivative of a sine x over plus 1 over 1 plus cosine of x can be rewritten the following way. Given that 1 plus cosine of x is a constant being multiplied, a multiplied constant, we can rewrite that outside of the derivative like this, just to make things as clear as possible. And now we're doing the partial derivative with respect to a of a sine of x plus 1. And sine of x is our constant in our situation. And 1, this 1 here, if you do the derivative of it, you get 0. So I'll cross that out. That's just 0. If you do the derivative of a with respect to a, you get 1. You multiply that by sine of x, you get sine of x. So therefore, this partial derivative ends up being equal to sine of x multiplied by 1 over 1 plus cosine of x, which is sine of x over 1 plus cosine of x. Now, if I put this back into the integram, so f prime of a, we can say is equal to the integral from 0 to pi over 2 of sine of x over 1 plus cosine of x dx. And now we just have a pretty basic Calc 2 probably integral, where if you let u, some new variable, this is a dependent variable now, not an independent one. I cue the biology majors screaming in the comments, oh, he said independent and dependent variable, he must be talking about the size of gill lungs or something. But gills don't even have, they have, fish don't even have, wait, what? So this integral is really the one that breaks me here, you can clearly see. If you let u equal to cosine of x and do the derivative of both sides, of course implicitly, and then divide both sides by negative sine of x, I just put the negative on the numerator, you get negative du over sine of x equals to dx. And now let us rewrite the integral in terms of u. Not me actually, but well you. So f prime of a can be defined as the integral of sine of x. Instead of dx, we can write negative I'll write it in green to make it stand out. Negative du over sine of x. And instead of our denominator 1 plus cosine of x, that's just 1 plus u, isn't it? And our limits from 0 to pi over 2, we can write them in terms of u, why not? So if I were to write u as a function of x, u of x equals cosine of x. If you sub in x equals 0, u of 0 is cosine of 0, which is 1. And u of pi over 2 is cosine of pi over 2, which is 0. So we end up with the limits going from u is 1 to u is 0. And for those of you Calc 1 students, perhaps early A-level math students out there, who are saying, hey, why does he have the lower limit on the top and the bigger limit on the bottom? Well, you're allowed to do that. And this won't actually be much of an inconvenience, because after we cancel out these signs, well, these not like the plus and the minus sign, S-I-G-N, I mean S-I-N-E. That's what I mean by sign. And then put this minus in the front. So f prime of a, why is my software bugging, is equal to the negative integral from 1 to 0 of 1 over 1 plus u du. Now, if I have a negative in front of the integral, it's basically, this allows me to switch around the limits. So now I'm going from 0 to 1 instead of 1 to 0. And it's a positive integral, of course. And this is as easy as our integral today will get. We get the natural log absolute value of 1 plus u, of course with the limits from 0 to 1. So f prime of a is equal to all of that absolute travesty. I'll write a in red, of course, of ln of, well, if you sub in 1 into u, you get ln of 2, not ln of degenerous. And if you sub in u equals 0, you get ln of 1. And really that is ln of degenerous, because this happens to be 0, and you can cross that out. So f prime of a equals ln of 2. If you were to do the integral of both sides, the reason we do that integral like this, I'll just put it in blue in respect to a, is so that we can get back to our f prime of a. Because ln of 2 is a constant multiple, I'll just put it outside of our integral with respect to a. So this integral here cancels out with the prime, and you're left with f of a and no prime, because like I drank all of it. And on the left hand side you get a times ln of 2. Of course, plus c, we can't forget this constant of integration. The reason we need this plus c is because we are working with an indefinite integral. So remember from previously, the original definition of this f of a that we had assigned was, get it, assigned, was the following integral with respect to x, of course. This one. Yeah? Now, what value could we sub into a to make this integral like as convenient as possible? Unfortunately, I couldn't find any a value. Of course, you could sub in a equals 0, but then that just gives us capital I, and that's what we're trying to find. We don't know what capital I is. So why don't we try out with a equals 1? So f of 1 is equal to 1 times ln of 2, which is ln of 2, plus c, which is equal to the integral from 0 to pi over 2. That's not pi. You can see my software really bugging out right now. It's some sort of lag. And then on the inside we have sine, 1 lot of sine of x, plus 1 over cosine of x plus 1 dx. And for this, we're going to have to use another substitution. Let's just use a Weierstrass substitution, but because I've said the word t 50 times, I'm in Britain right now, I'm getting a little bit like thirsty, so instead of using t, let us use what letter? I've used so many letters. I'm not going to use Z because we're not touching complex analysis. I won't use Y because why not? I'll probably use W. So let's let W equal to tangent of x over 2. Once again, we're taking a Weierstrass substitution. And you may ask, why didn't you do this to begin with? Well, I did all the way up here. But that was for our second method, our fastest method to do it. Here, I'm trying to think of the slowest possible method to do it, and that is what we're doing here with this Feynman's trick. Well, I'm just going to do the exact same thing that I did with the previous method, where I apply arctan to both sides and multiply by 2. So arctan of W equals to x, and do the derivative of both sides, and you end up with the following there. And if I were to redraw the triangle again, redraw every single possible detail, including the length of the hypotenuse that you worked out using Pythagoras' theorem, and then write very nicely on the bottom, sine of x over 2 is equal to the opposite over the hypotenuse, and the cosine of x over 2 is equal to the adjacent over the hypotenuse. And so sine of x, using the double angle formula, is equal to 2 times sine of half of the argument multiplied by cosine of half of the argument, which in our case is equal to 2 times w for win, of course, over root 1 plus w squared, multiplied by cosine of x over 2, which is 1 over root 1 plus w squared. And if you simplify this, the top is just 2w. For the bottom, you're squaring a square root, so the square root evaporates into thin air. Well, I'm in my room right now, so the air is probably dense. Now, what do? How about we need cosine of x as well, because our integral isn't just for sine of x, it's for cosine of x as well. Why did I draw an arrow? I didn't need to. Cosine of x is equal to cosine squared of half of the angle, or the argument, minus sine squared of half of the argument. And that is equal to, well, we already worked out the other method. It's just equal to 1 minus w squared over 1 plus w squared, except we had t that time. Now we have Fanta instead of t, unfortunately. So we can write that f of, let me write it in black to keep consistency, f of 1 in red, once again consistency, equals ln of 2 plus c, which is once again equal to the integral from 0 to pi over 2, of course these limits applying to x, not to t, of, let's see, we had sine of x plus 1 over here in this integram here, sine of x plus 1 on the numerator, and cosine of x plus 1 on the denominator. Now, let's work with the numerator first. Sine of x plus 1 is equal to, well, this bit here, plus 1. So 1 plus, I'll put the 1 on the front, why not? 2w over 1 plus w squared. And then on the bottom we had 1 plus cosine of x, which is 1 minus w squared over 1 plus w squared. Finally, to close the integral, we need what dx is. And dx is, over here, 2 times 1 plus w squared. Sorry, 2 over 1 plus w squared dw. And the 2 we can bring to the front. So then f of 1 is equal to 2 lots of the integral. Should we change the limits from x to w? I think it might save us some time. So let's do that. So let's define w as a function of x rather than as just a plain old variable. So that if we sub in the limits 0 and pi over 2, well, sub in 0, you get tangent of 0, which is 0, and sub in the limit pi over 2, you get tangent of half of pi over 2, which is tangent of pi over 4, which is 1. So w goes from 0 to 1, and then we have the rest of the function. So how do we do that? I think it's quite simple actually. The numerator we can just keep it the same. Nothing happens to the numerator. I'm sorry, no fireworks. The denominator, though, that's a special bit. If we distribute this 1 plus w into there and into there, you get 1 plus w squared plus 1 minus w squared, and of course dw. And the exact same thing that happened the previous time we did this integral occurs, where the w's cancel out and you're left with 2 on the bottom. So this entire thing on the bottom is just equal to 2, and so this 2 cancels out with the 2 on the outside, and you're left with simply, I'll just rewrite the integral in a nicer way, from 0 to 1 of 1 plus 2w over 1 plus w squared dw. And this is a basic, probably, maybe not Calc 1, but still quite a basic integral. Let me just write these ones in red. That's better. So f of 1 is equal to, well, I think I will split the integral into 2 integrals. Why not? It's not like it makes it quicker. It's not like it makes it look nicer. I have no reason to do that. I just want to, it looks nice. Okay. Plus, so the integral of dw, that's what 1 times dw is, plus the integral of 2w over 1 plus w squared dw. Why are my pen marks going all over the place? Now, usually the standard practice is to put this 2 on the outside. I'm not going to do that. You really don't need to. It's clear that this bit here, this integral, is equal to w evaluated at 0 and 1, which is equal to 1 minus 0, which is 1. So we won't worry about that for now. How about this integral? Well, quite a basic integral. In fact, I can do it just by inspection, just by guessing and checking. But just for people out there who are new to calculus, just for you guys, nobody else, I'll do a substitution. I don't need to, but I really do care for you. So let's let 1 plus w squared equal to a new variable. Let's call that variable, what should I call it? Greek letters. Let's call it alpha. So if you differentiate both sides implicitly, you get 2w dw equals d alpha. And what do you notice? Well, we have 2w times dw here. That is equal to d alpha, isn't it? So this integral, we still have the 1 from earlier. Let me write f of 1. Don't worry about that. Plus the integral from w equals 0 to w equals 1 of what? Of, well, the 2w dw is just equal to d alpha. And the bottom, 1 plus w squared is equal to alpha. You're integrating 1 over alpha, which is equal to ln of alpha. So you get 1 plus ln of alpha, of course with the modulus, evaluated at the limits w equals 0 and w equals 1. And so what is that equal to? Well, if you change the limits from w to 1 for a second, let's write alpha as a function of w, why not? So if alpha of w is equal to 1 plus w squared, this implies that alpha of 0, so that's when w equals to 0, that's equal to 1 plus 0 squared, which is 1. And alpha of 1 is 1 plus 1 squared, which is 2. So our limits change from 0 to 1 into 1 to 2. So our limits are alpha is 1 to alpha is 2. I'll just write it like this. So what do we get? We get, of course, the 1 from earlier. I'll write it in black for consistency. Plus the ln of 2 minus ln of 1, and ln of 1 is 0. So we have 1 plus ln of 2 is equal to f of 1. What is this f of 1 exactly representing? Well, if I scroll up as a reminder, f of 1 is equal to ln of 2 plus c, which is equal to our, so that integral that we have. Not the original one, just, So I'll rewrite that here. So f of 1, I'll write everything in black now, is equal to, what was it again? I forgot. ln of 2 plus c, sorry. Which is equal to 1 plus ln of 2 that we worked out. I'll write that in blue. So, what do you notice? These two things cancel out. C is equal to 1. What is f exactly equal to? F, we said it was a variable of a from earlier, and we defined it as, what was it? We had two definitions for it. We had the original one with the integral, and the one that we found out after doing the integral under the differentiation under the integral sign. What was it? Where is it? Here. A ln 2 plus c. So, a ln 2 and plus c. C we already worked out as 1. And this, remember, is equal to the integral from 0 to pi over 2 of a lots of sine x plus 1 all over 1 plus cosine of x dx. Sorry, excuse the lag. I'm going to have to complain to Steve Jobs about this one, even though he'll blank my phone call. Now, finally, what was our original integral actually equal to? Well, here I've clearly written, if you need to zoom into the screen or whatever you need, f of 0 is equal to I, not equal to 1, it's equal to I, which is our original integral. So all we need to do is sub in a equals to 0. So I, our original integral, is equal to f of, 0, which is equal to 0 lots of ln 2, of course plus 1, which is equal to 1. So therefore, I've proven it to you 3 different ways. Well, not proven, I've shown it to you 3 different ways. How can you not believe that 1 plus cosine of x dx then is equal to 1? Thank you very much for watching. Please like, subscribe, share, and do anything you can. Comment as well. Give some feedback. Please let me know what integral you want me to do next. If I don't know how to do it, then it's nice for you to give me a clue to, And thank you for watching. Of course, before you leave, if you leave, feel free, but before I end off this video, I'll just summarize it quickly. So, just from the very start, we had said from the previous video, this theorem here, I guess you could call it theorem, whatever, and I said that, what if you sub in a and b as 1? And what's the issue with that? The issue is, you end up with a situation where you have to divide by 0. And the solution to that is you use limits to calculate all that junk, that nonsense, and the limit ends up evaluating to 1. So therefore the integral of 1 over 1 plus cosine of x dx evaluated from 0 to pi over 2 is 1. So that was the first thing that I had. I had a problem and I ran into it and then I solved it, which is very good. The second thing was, well, what if, let's say you didn't have this nice little statement, this nice arrogant, whatever it is. What if you didn't have that? What if you just had the integral on its own? How would you solve it just with a simple, not a simple, but a substitution? Well, I used the Weierstrass substitution and it worked out very nicely to be 1. 1 over here and 1 over there. Really nice, because it's a good number, 1, isn't it? It's plenty of trophies plastered with that number everywhere for all of my viewers out there, I'm sure. And then the third thing was, what if we went absolutely ballistic and found the literal longest way? Maybe it's not the longest way. You could probably take this to some weird coordinate system, which I haven't learned about yet. But just within my capability, what is the longest way that works that you do this with? And that is with this Feynman's integral. You integrate, you differentiate under the integral sign. You end up with f prime of a as ln of 2. You integrate both sides. And then you end up with a constant of integration, which you find the value of as being 1 by doing yet another integral here using a Weierstrass substitution. In fact, what if you had a dream where you used Feynman's trick, and then you needed to do another integral, which you could do Feynman's trick for as well. That's just confusing, but luckily I don't have those types of dreams. Now, after working out that integral to be ln of 2 plus 1, we could conclude that c, our constant of integration, was equal to 1. So I could rewrite our f of a in terms of a, and, well, c was just 1. So now we were only dealing with one unknown, basically. And then all I had to do was substitute a equals 0 to get our original integral back, and I got 1. So that's perfect. Thanks for watching, and good night.